Welcome back to ECE 220. We have quite a few announcements to make for today, and most of them involve dismissal of class period. So the next couple of Fridays you're getting off. You have this Friday is one of those, and that's after you've taken your exam number 3, which is tomorrow in here. Group A, you're still doing lab 4s this week. Group B, your lab 3 report is due today. And then you will have your pre-lab for lab number 4 on Saturday. And mixed in all of that are some dismissals of class. No class Friday, no class Monday, and no class next Friday, but sandwiched between those, Group B, your Lab 4 is next Tuesday, right after the Veterans Day break, and the class, your homework number 11 is due, and that I need to assign. I don't even think you have access to that, right? I don't think I've created it. I was hoping you would give me some leniency while you're cramming for exam 3 tomorrow. I'll try to get homework 11 assigned today if you are breezing through exam number 3 material. Today what I want to do is continue with chapter 8, which is dealing with RLC circuits. Let's finish up the 3 different types of responses. We've already covered overdamped, which corresponds to where are your poles in where are the roots of this characteristic equation when you have an overdamped response. Do we remember? Overdamped, they're real and unequal. Last time we just talked about underdamped, which is when we have complex conjugate roots of that characteristic equation. Today we want to look at what happens just sort of briefly. What is the structure of the solution when we have real equal roots to that characteristic equation? That's the critically damped scenario. It's the same parallel RLC circuit, it just differs in what these parameter values are equal to, R, L, and C. And last time maybe I confused some of you by saying what makes this a tank circuit. I was just trying to get us comfortable with how we might introduce oscillatory behavior. When we have a tank circuit, that R goes away. The resistance goes to infinity. We open up that particular branch, and now we just have this oscillation of energy stored in the magnetic field of the inductor and just tossing that back to the energy stored in the electric field of the capacitor. And that just goes back and forth in this sinusoidal manner. The sinusoidal behavior depends on the L and the C values. The natural frequency is 1 over the square root of their product, L times C. If we now introduce some resistance, depending on how much we introduce, throws us into one of the 3 different patterns. If we gradually is maybe difficult to comprehend when we're going from infinity to gradual, but we're coming in from a larger value of R to introduce damping into the circuit. We go from purely oscillatory to damped oscillatory. Then as we make R and R smaller, in this case, we now get into the critically damped and then the overdamped. We're talking now today about the critically damped, where we have 2 real equal roots of that characteristic equation. You can use KCL and Eli to find the dynamical behavior of this system in a second-order differential equation. It's second order because we have two energy storage devices, the inductor and the capacitor. We can assume a structure for that solution for I sub L of t. We could say, oh, that's A e to the st. Doing that, substituting that into the differential equation, then imposes constraints on that frequency parameter S. S now needs to satisfy this quadratic equation, S squared plus 1 over RCS plus 1 over LC, and what happens after that all depends on those three parameters, or it depends on where are those roots located. Are they complex conjugate? Then we have oscillation. When we have that imaginary component, think oscillation. When they're real, then whether it's overdamped or critically damped depends on whether those roots are equal or unequal. If they're unequal, if it's overdamped. Today we want to talk about the case where they are real and equal. Or what if we have two real equal roots that arise from this characteristic equation? For example, maybe they're S equal minus 1 and S equal minus 1. They're two real equal roots. It always helps to just kind of, I think, visualize where these S values are in the complex S plane. And here we're saying, oh, we have now two poles right on top of each other. They're real and equal, and they're at a distance of 1 away from the origin in the complex S plane, and they're actually going in the negative direction. That's good because that gives us now this e to the minus t structure. If we now have our poles there, then we call that critically damped, and it's for a parallel RLC circuit. We now need to figure out what structure are we going to use for the solution to that second order differential equation. What's I sub L of t look like structurally as a solution? Is it going to be consistent with what we've been doing and just saying, oh, let's say we have A1 e to the S1t plus A sub 2 e to the S sub 2t. That worked in the previous two. In the one we talked about yesterday, we went through that derivation where A1 and A2 ended up being complex, and we said, oh, let's just not worry about that derivation anymore. Let's just assume the B version, B1 e to the minus alpha t cosine omega sub dt plus a B sub 2 e to the minus alpha t sine of omega sub dt. We had the exponentially damped sinusoids. Does this work? Is this solution going to work for us now? And now I'm maybe misleading you by saying we have an S1 and we have an S2, but in this case, what do you know about S1 and S2? We're saying that we're in the critically damped case, and now they are the same value. They're real, but they're equal. S1 is minus 1, for example. S sub 2 is minus 1. Now, this structure isn't going to work because the mode e to the S1t is the same in both pieces that we're adding together. We have e to the minus t and e to the minus t. We're not getting anything new with that mode or with that assumed structure. So this structure isn't going to work. It doesn't work since e to the S1t is the same as e to the s sub 2 of t, since we're now in the critically damped case where those two frequencies, s sub 1 and s sub 2, are equal. In our example, they were both minus 1. Another way of thinking of that is if you were thinking about not being the same, well, this mode, e to the s1 of t and e to the s sub 2 of t, are not linearly independent. In their structure. They're exactly the same structure. The strategy then to overcome this fact that they are no longer linearly independent is to make them linearly independent, and we can do that by introducing coefficients associated with those modes of powers of t. T squared, t cubed. If we need more, we just keep raising t to higher and higher powers. In this case, we only have two modes. We just need one unique factor. In this case, let's introduce a power of t which, for example, here it just needs to be t to the 1. If we had three real repeated roots, e to the minus 1, e to the minus 1, e to the minus 1, we would have to go with e to the minus t, e to the minus t, and t squared e to the minus t to give us some linear independent behavior. For this case of 2 real equal roots. Now the structure, when we have real and equal roots, or somebody might say repeated roots, we're going to now say, oh, that's d1 t e to the s1 t plus d sub 2 e to the s1 t. Here I will go ahead and be clear that s1 and s2 are the same. Now that we have a structure that has linearly independent terms, we can now solve for the unknowns d sub 1 and d sub 2. Just like we've had A1 and A2, B1 and B2, now we have a D1 and a D2. And I'm guessing the reason we don't use C's is so it doesn't get confused with our capacitors. So we have different variables, A's, B's, and D's, for these three different types of solutions. Now we need to find D1 and D sub 2 from the initial conditions. We have the structure, and if we can now look at the circuit or analyze the circuit and determine or are told what the initial current is through that inductor, we can now have one equation relating that value to D1 and D2. If we substitute 0 into the red structural form, what do we end up with? We have D1 times 0, e to the 0, that's just 0, plus D2, e to the 0, which is 1, so we have d sub 2. We immediately know what d sub 2 is from the initial current through that inductor. The other one takes a little bit more analysis. Let's now differentiate this new structure for I sub L of t, which is the result of having critically damped parallel circuit We now differentiate the first plus the first times the derivative of the second plus did I do that in an okay way? And if we can now find the derivative or the time rate of change of our inductor current at time 0, we now have our second equation that we can use. We now have d1. The middle term vanishes if we replace t with 0, and we then have our third term coming in as d sub 2s. We now have our two equations in the two unknown variables d1 and d2 that we can now use to find the actual expression for the inductor current. And that's when we have the critically damped solution, and that is when we have two real equal roots of this characteristic equation. Which structure we assume depends on what we end up with for roots from that equation. Now we know how this circuit naturally behaves if we initialize the inductor current and capacitor voltage in the parallel RLC form. We have three different ways that it can behave: overdamped, critically damped, and underdamped. Now let's force this system with a constant input. And for this discussion, let's assume that we're exciting this parallel RLC circuit with a constant current source in parallel. That wire that has the switch in it is closed from -infinity up to 0. If that's the case, what are the initial values for the inductor current and the capacitor voltage, or the voltage across any of those three parallel elements? What's the current flowing through I sub L if that switch is closed? This is for t less than 0. It's set there for a long time, and what has it decided to do? No one wants to volunteer. What's that resistor done to any energy in that system? It's set there forever, for an infinite amount of time before 0. What's that resistor done to any energy that was present in that system? It's dissipated it all. We have no current flowing in the inductor. We have no voltage dropped across that capacitor or inductor or resistor. This is now 0 and 0. Let's make it a little more interesting. Let's open up that switch. What happens as t goes to infinity? Well, now we have the current source in play, and we have the three circuit elements. The source is constant, and it's now been in this scenario for a long time on the other side of the origin. As we march off to infinity in time, what's going to happen now? How do these circuit elements respond to DC sources? What happens to our inductor? It slides across the floor. Hopefully that didn't come through in the mic, but somebody's moving upstairs. It shorts, doesn't it? So the L becomes a wire. What's the capacitor do? It charges up and becomes an open circuit, so that now we have something like this. And what do we know is happening now? What do we know about I sub L at infinity? If you want, you can do a current divider between R and 0. And what are you going to find? You're going to find all of that current that's coming from the source going through that inductor. Path of least resistance. That current's going through that short-circuited wire, which is the consequence of that inductor seeing a DC source. What's the voltage if we needed it? We have a wire. What's the voltage dropped across a wire? 0. All right, so now we know the final values. We know the initial values. We want to figure out, is anything happening between? Something has to, because the current goes from nothing to I. How does it get there? Does it go nicely? Does it kind of overshoot and undershoot? Does it get there in another way? And what would you guess we have for choices in how it goes to that final value? We still have this RLC circuit. This is what we need to analyze for t greater than 0. We haven't yet gotten to steady state, so we're not yet at infinity. What kind of behavior do you think is going to present itself in this parallel RLC circuit? Luckily, we're not going to have to throw away everything we just talked about the last 2 or 3 days. It's going to have one of those 3 behaviors as it approaches this limiting value of I. It's going to be either overdamped, underdamped, or critically damped. So we get to keep those 3 structures. Now we just have to figure out, how do we decide, or what is going to be involved. So now if we examine this, how do we find how this circuit is going to behave? We need to find its dynamical behavior. We need to analyze this circuit. How do you want to analyze it? I'm not going to do mesh. I'm sorry. I'm going to do KCL. We have a common voltage. Let's now do KCL. And what do we see? Well, we can say that current source is going into the node. I'm writing a KCL equation here. And let me just assume all the other currents are going down. I now have V over R. And what do I probably want to focus on in terms of variables? My state variables, which is capacitor voltage and inductor current. So I'm going to leave I sub L, that's the inductor current, and I tells us we have C dV dt, current going down using the passive sign convention through that capacitor. We need to get rid of one of those variables. Let's use Eli. We've done this before in the natural response. Now we have the step response. Eli allows us to say or establish this relationship for the inductor, current and voltage. And now we have I is equal to L over R di sub L dt. I'm simply replacing V with this L times the first derivative of the current. I sub L we want to leave alone, since that's the variable that we're interested in. And now we replace V with L di dt. Now we have an LC second derivative of I sub L with respect to time. And this shouldn't surprise us. Now it looks very similar to what we've seen before. It just has a forcing function, the current source. And I might call this many different things. I might say, what's the governing dynamical equation? Or what's the equation of motion? Or what's the differential equation associated with this forced parallel RLC circuit? Now let's maybe get it into a standard form by making the coefficient of the highest power of the derivative equal to 1. We can do that by dividing all terms by LC. Doing that and putting the terms, the derivatives, highest derivatives on the left, we end up with second derivative of I sub L with respect to time plus L over R divided by LC gives us 1 over RC, first derivative, plus 1 over LC I sub L, and that's equal to I divided by LC. And I might refer back to that equation, so I'm going to call that equation star. Now we want to solve this differential equation. Second order differential equation. Let's just step it through like we would in a math class. Let's break this solution into two pieces. Its homogeneous solution, which we've already been doing with the natural response. That's the homogeneous, and we'll look at the particular solution. We'll add them together to get the total or complete solution. So we're doing the solution to this differential equation. To obtain the homogeneous equation, what do we need to do to star? If we want the homogeneous equation, to find the homogeneous solution, we need to set the source equal to 0. And now we have what we've just spent the last few periods talking about, the natural response. And I'm going to call that I sub L, and if we wanted to, we could write that equation down again. We now have, but now we want it to be just the first part of that. It's the homogeneous piece. And what's the structure going to be? And there you can always answer with it depends, right? It depends. Usually that's a pretty fair answer to any question that somebody might ask. If they ask you a question, you might just say it depends. Well, in this case, that's a valid response, and it depends on what these parameters are, R, L, and C. What are their numerical values? Let's just assume, I think, the more interesting case, which is when we have complex conjugate roots. And what case does that give rise to? What's the structure for I sub L sub H, the homogeneous solution to this parallel RLC circuit when we have complex conjugate roots. And again, I would maybe suggest that you just think about where these roots are, and as I suggested before, you might see these labeled by X's in the complex S-plane. Now we have these X's with imaginary components. They're complex conjugates. How far are they into the left half plane? Complex. This distance is alpha. How far away are they? What's their hypotenuse from the origin? That's their natural frequency, omega sub 0. And now if you remember this picture, you don't really have to remember the formulas, you just have to remember geometry and trig. Now, their damped frequency of oscillation, this distance, is omega sub d. That's the picture that you can envision when you're thinking about the solutions to this characteristic equation. If we had overdamped, where would those X's be? This is the underdamped case. Where would they be in the overdamped case? And we could have assumed this structure. They would now be real and unequal. If we were in the critically damped case, that's when they are real and equal. And I'm showing them offset just so that you remember that there's two in that location, but they're right on top of each other. If we now have the values of S that satisfy this second order polynomial, this characteristic equation, what do we now know the structure looks like? It's our exponentially damped sine and cosine expression. We now have this B1 e to the minus alpha t cosine omega sub dt. And now you can say, oh, the damping is how far into the left half plane we are. That's the alpha. Then we have a plus b sub 2 e to the minus alpha t. I would have written this on the same line had I not scribbled that figure there, sine omega sub dt, where S1 and S2 are this minus alpha plus and minus j omega sub d. Those are the values, and in terms of our parameters, if you can find alpha, that was 1 over 2 RC. Omega naught, that's 1 over the square root of LC. And a lot of this, those two, no, I think omega naught, Dr. Marcelin, has left off of your formula sheet, but you have alphas for parallel RLC and a different alpha for series. And we'll talk about the series, wow, the next time I see you in a lecture setting, which is on Tuesday. Right, almost a week. I don't know if I may have withdrawal from that. But you'll be here in intense mode tomorrow for the exam. So, Omega sub d, how do you find that? Once you have omega naught, 1 over the square root of LC, and you have alpha, you can draw this picture and find omega sub d. That is just from the Pythagorean theorem. Alpha squared plus omega sub d squared is omega sub 0 squared. That's relating the hypotenuse of a right triangle. And you can solve that for omega sub d. What I'm suggesting is don't try to just keep all of these things in your head necessarily, but just realize that you have a right triangle, and now you know that a squared plus b squared is equal to c squared. C is your hypotenuse. That's the natural frequency. B is your imaginary component. That's omega sub d. And alpha, or A, is your real component. And you can now solve this. Boy, this is getting kind of messy. But you can interpret this. You know what I'm doing. Omega sub d is now the square root of omega sub 0 squared minus alpha squared. And instead of trying to memorize that crazy formula, you can derive it. You can say, oh, this is what happens. That's our damped frequency of oscillation, omega sub d. Once you have alpha and omega sub d, you can write down this structure. But that's as far as you want to go. You want to leave the b's alone until you have the complete solution, and the complete solution needs the second half, which is the particular solution. And now we need to put our source back into the circuit. The particular solution is when I is not equal to 0. And how do we find the particular solution? We look at how this differential equation is being excited. What's the source? What's the structure of that source? In this case, it's a constant. So we would expect our particular solution to be that same structure. We would expect the particular solution to be a constant. So now we're just going to say, oh, let's let I sub L of P, I sub L particular be K, a constant, since this is now the same structure of our forcing function. Where our forcing function is the constant value of our current source, and that's I. That solution has to satisfy our governing differential equation, which this is why I labeled it with a star. I sub L sub P must satisfy star. And if we go back here and find star, here boy, there he is. Here's star. We need I sub L as a constant to satisfy that. We differentiate a constant, it goes away. We differentiate it again, it goes away. The first two terms are gone with that assumed structure for I sub L particular. We just have the third and fourth term on the right, which says we have 1 over LC times I sub L particular, which we said was K. So now we have 1 over LC times I sub L particular, which we said was K, which is equal to 1 over LC times I. The 1 over LC's cancel, and we see that our constant is just the source value, I. And now we're ready to put together our total solution. Our total solution is the homogeneous plus the particular, and we selected based on the values of R, L, and C. We said let's just look at the underdamped case. So now we have the exponentially damped sines and cosines. B1 e to the minus alpha t cosine omega sub dt plus B sub 2 e to the minus alpha t sine omega sub dt plus the particular solution, which was K, but now we've found that to be I. And we already know alpha and omega sub d from the solution to that characteristic equation. Do you see that this part right here would change depending on where your roots of that characteristic equation are? If they're overdamped, you have the A's. If it's critically damped, you have the D's. If it's underdamped, you have the B's. Now we can solve for those unknown B's by our initial conditions. We find the initial current from this structure. We plug in 0 everywhere we see a T, and what do we end up with? The sine piece goes away, the cosine goes to 1, the e to the minus alpha 0 goes to 1. We have B1 plus I. But in this particular circuit, what was I sub L of 0 plus? When we had that switch closed from minus infinity to 0, and then we opened it at 0. What was it before 0? What was our current in the inductor? It was 0. We combine those. We now know that B1 plus I is equal to 0, and I is not the identity matrix. I is the value of our current source, or B1, is now minus I. And using Eli, we now can find the initial condition on our time rate of change of the inductor current. That is now V at 0 plus divided by L. And V at 0 plus in this example was 0, so now we know that the time rate of change of our current at the origin is 0. What is it from our equations? Well, now we have to differentiate this with respect to time, that structure, I sub L of t, and then evaluate it at 0 to find the b's. So let's now differentiate I sub L of t, the total solution. That's now minus b1 alpha e to the minus alpha t cosine omega sub dt plus b1 e to the minus alpha t, and what's the derivative of cosine? Minus sine, and we're going to have that argument to differentiate. So this is now sine omega sub dt. That's the first piece differentiated, plus b sub 2, and it also is the exponential, so we now have the minus alpha b sub 2 e to the minus alpha t sine omega sub dt plus b sub 2 e to the minus alpha t omega sub d cosine. And what happens when we differentiate the constant? I. That's 0. So this now is all of our terms for I sub L prime. We can now set that or evaluate that at time t equals 0. The sign, or the terms that have the sign piece, go away, and we're left with minus alpha b1 plus omega sub d b sub 2. And from our circuit, from the initial conditions in this example from the circuit, we know that's equal to 0. If somebody had established initial conditions differently, you would now put those values in here to help you solve for B1 and B sub 2. Now we can solve for B sub 2. And that's now alpha B1 over omega sub D. And we've already solved for B1. That was minus I. And now we know what B sub 2 is. Or we could now write this complete solution as minus I e to the minus alpha t cosine omega sub dt plus b sub 2, which is minus alpha I over omega sub d e to the minus alpha t sine omega sub dt plus I. And that would be our solution to a forced, that's the step response solution of this parallel RLC circuit excited by a current source of magnitude I, and it's constant, and the R, the L, and the C have to be given in a manner such that they give rise to complex roots to that characteristic equation. Oh, it's time to wake up. Whew. That was... Do you see how I could, or it could be varied? We could have different initial conditions, so this 0 right there might be different, and the 0 right there might be different. You might have different behaviors here, all based on what you're doing with your solution, or what you found from the solution of your characteristic equation. Which one goes with what? And now these are written in terms of x because you may need to be solving for current. So now your x would be a current, or you may be solving for a voltage. But you have these structures, and because they have these x's at infinity, that tells you that you are looking at a forced or a step response. But if you have a natural response, what's happening at infinity is going to be zeros. And those then can just be eliminated. But it already now establishes the expressions that you can use to evaluate your unknown coefficients. You now need to find your initial, and they're written in terms of not really throwing the switch at 0, but throwing it at t0. So you may have this switch thrown at at 2 or 6. That's the T0. That's the reason for this shift in the arguments of time. If the switch is at 0, that T0 becomes 0. And these formulas collapse down or simplify a little bit. And what we will do next time is we'll find alpha. We found star. Here, boy. We'll find another pet, alpha, for series. We've already found, and that's not Siri. I was going to get my phone out and ask Siri for out. We've done the parallel. We've done everything except figuring out what's the structure of our characteristic equation when we have a series RLC circuit. I'm going to do something odd and let you go early, unless you have questions. Question? Do we have extra credit on the exam? Do we? Do you want extra credit on the exam? We're done now, okay? Bye.